Good afternoon, everyone. Appreciate you joining in for the webinar. As Mark said, we're going to talk about coatings and pottings. Before I get started, though, I wanted to quickly mention that next month, on March 20th, DFR is having our reliability conference on the Inner Harbor of Baltimore. And if you would be interested in registering for the event, you can either email me at gcaswell@dfrsolutions.com and I'll send you the link information, or you can go directly to the link shown there at the bottom of this page. It's going to be a good lineup of speakers, and you'll see that I'm the last speaker there, and I'm going to talk about what I've learned in 45 years in the electronics industry, which theoretically should be quite comedic. Okay, the abstract that I put together for this webinar kind of talks about the fact that I'm going to address coefficient of expansion issues, delamination, cracking of conformal coating, de-wetting, pinholes, orange peel, all these different failure modes that can occur with conformal coating. We'll look at potting in a similar fashion, paying particular attention in both cases to the glass transition temperature of the materials involved. We'll also look at whether curing cycles done improperly, what the effects might be. And then we're going to end up looking at some of the new superhydrophobic materials that are kind of making a lot of headway now in the electronics industry with respect to conformal coating. Before I get into it, kind of a mantra for me is that there's a need to clean your assembly before either coating or potting the assembly, and I'll explain why. We're worried about contamination on the surface of the board. That might be ionizable contaminants that are soluble in water. It might be hygroscopic contaminants. Particular focus when we look at cleanliness, we look at anions, and we specifically kind of home in on chlorides and bromides due to where they can come from. Cations, when we look at those, are to help us in identifying the source of the anions. For example, if you get Cl coupled with K, you can get KCl or salt from human sweat. So, that's one of the reasons that we look at the cleanliness. If you look at where do they come from, okay, chlorine, for example, comes from the board fab process, might come from flux, might come from rinse water, might come from human handling. An example I have is when I was looking at some handling of some assemblies at a manufacturing facility in China recently. It was about 95 degrees Fahrenheit and 90% humidity in this manufacturing area. And clearly I was sweating, but most of the operators were fairly comfortable. But still, when their oils from their fingers got onto a certain portion of the assembly, it caused failure. And so, we had to institute a policy of special cotton gloves to eliminate that issue. Bromines come from printed board fabrication. They're used as flame retardants. Some of the other elements that you see here come from, cleaning, the rinse water, and then weak organic acids pretty much come from the solder flux that's used in your process. So this page kind of shows you some of the different places in a typical circuit board fab facility and what some of the materials are that get introduced. You can see that hydrochloric acid is used in a couple of locations. Methylene chloride is used as a solvent. You can get different chloride-based materials in the etching process. All of these need to be cleaned. One of the things that we see fairly often is that brand new bare circuit boards coming into a manufacturing facility have residues left on the board because they were not completely and properly cleaned, and this starts you off in trouble. And then when you go through an assembly process, you add to it, and then if that's not taken care of and cleaned properly, it can create real problems during the conformal coating activity. If we look at fluxes, you can see that there's a number of different flux nomenclatures. Most that are used in the no-clean arena are the rosin-only or RO type materials, but there are others that are more mildly activated that really do need to be cleaned off the surface of the board, both from a cleanliness and dendritic growth potential, but also because the residue from that flux will create a barrier between the conformal coating and the board surface that impedes adhesion. And we'll talk a little bit more about that shortly. This is right out of the J standard. It shows all the different types of flux materials and whether they are low activity, medium, or high activity level materials, and you can see that they exist in all categories. The typical flux used for a no-clean is ROLO, which is the least active, but that's not always the case. And so you need to pay attention to what that residue is. And, you know, I think, again, no matter what one you choose, cleaning it before conformal coating is absolutely necessary. You can have different types of things get on your board surface from human contact. You can also have materials get on your board surfaces from cleaning chemicals that are close by in the manufacturing area, maybe some outgassing that's going on. Maybe also in your use environment. You know, industrial pollutants is a big one. This is something I'm going to talk about more, where we address the types of conformal coating needed to impede these types of pollutants. Not all of the different types of coatings work. Maybe you're exposed to the salt air near evaporated seawater. That can also have a distinct impact on the selection and performance of the conformal coat that you choose. Handling in sweat, still a major issue. The main concern that we have regarding sweat is that it's a source of chloride, which left on the surface, you know, is going to cause a problem when you put conformal coating over it. So let's think conformal coating now. Why do we do it? It's a layer that we put on top of the board to protect it from moisture in the air or other contaminants that might be in the air or near where your product's going to be implemented. What we want to do is keep the insulation resistance as high as possible. If that is impacted, then you can have electrical issues such as crosstalk, leakage, signal losses, and possibly even shorting. Getting rid of that moisture again, or stopping it from penetrating to the surface, is also going to help with reducing metallic growth. Excuse me. Dendrites and corrosion. So again, keeping things clean on the surface of the board is very, very useful in getting good conformal coating performance. These are the basic 5 different types of conformal coating used today. We'll talk about the newer ones later in the presentation. But epoxy is not widely used, but it has good adhesion. It's a little bit harder material once it's applied to the board. And it's very difficult to rework. Urethane is the material that is highly chemical resistant. So if your product is going into an area, say, like the Texas coast near the oil refineries, you know, urethane is likely the best choice because of its chemical resistance. It provides an acceptable moisture barrier and has good adhesion. Again, it's difficult but not impossible to rework. Acrylic is used in about 70% of all applications today. It's got good adhesion, poor chemical resistance, and very good in high moisture resistance. So again, for most applications, it's very viable. It's also easy to rework and fairly low cost. Silicones are tougher to get good adhesion, low chemical resistance, and excellent moisture resistance. They're higher cost, and as you'll see in a subsequent slide coming up, you have to apply it about 2 times the thickness. So that actually increases your cost automatically by forcing that doubling of the thickness. Parylene is an approach that's applied using a chemical vapor deposition technique. Very good adhesion, gets underneath all the components, completely coats them, doesn't create a barrier that can impact coefficients of expansion. Excellent chemical and moisture resistance. And there are now, as I show on the right-hand side, rework procedures for parylene that make it, a little bit more palatable as an approach. The only issue with parylene is because it's chemically vapor deposited, it's about 10 times the cost of the other approaches. But sometimes, total coverage is an absolute requirement. A lot of different ways to apply conformal coating. The most typical way is spraying, usually robotically controlled, say with like an Asymtech system or something of that nature. But you can also apply it with brushing. I've just found that brushing is not anywhere near as consistent as a spraying process. Dipping is an excellent way of applying a coating in, depending on how many dips you do in each orthogonal axis. The key to a dipping process is that your masking has to be perfect. If there's any small pinholes or anything in your masking and you put it into a full dip process, the conformal coat will find a way to get to either a component or an area of the board where you don't want the coating to be. So, again, the masking operation becomes the driver. A lot more selective coating now where only certain parts are coated and portions of the board. I'm not sure that I'm a champion of that approach. I guess it depends again on the environment you're going to put your assembly in, but it still gives, if you do that, it gives many paths for moisture ingress to later cause a problem. Inspection of coated boards is typically accomplished using UV or black light. When you expose the surface of the coating, it fluoresces. So you get an appearance like you can see in the picture here, where the white areas are areas where there's good coverage, and darker areas are areas where it's either very thin or uncoated, but it gives you a good indication of where you need to touch up when necessary. Proper curing. I'm going to talk about this quite a bit. You can use 24 hours in room air, for example. You might use UV curing. Might be temperature involved, might be temperature and moisture to properly cure a particular composition. Time to cure is a function of the coating and is a critical step. I just recently did an audit of a facility in China and noted that the conformal coat was supposed to have, based upon the data sheet, was supposed to have a 2-hour cure at 76 degrees C. I watched a board enter the curing oven and watched it come out 4 minutes later. At the end of 4 minutes, the surface was still extremely tacky, at which point the only obvious method for curing was to let it sit for 24 hours. Within the hour, those boards were being moved across town to a different facility to integrate them into the final assembly, which meant that the coating was going through subsequent manufacturing operations long before it was cured. That's problematic. UV curable coatings, you may have to have what's called a bump cure on top of that to properly cure the areas that are not exposed to the UV. Max temperature, in our opinion, should be less than 100 C. So that's, and I'll point out why that's a potential issue, both for conformal coating and potting. You may want to do some outgassing assessments in room air before going through temperature chamber to make sure that you've completely outgassed the conformal coating before the fully cured cycle is completed. And you have to look at what your environmental exposure is going to be to make sure that your cure cycle is optimum for that. Improper conformal coating put on the board can impact different types of parts. You can break them. And what it is the coefficient of expansion mismatch between the conformal coat, the part, and the circuit board. And this is all very sensitive to thickness. And you'll note here that acrylic, urethane, and epoxy are all pretty much the same. They all seem to be about a 2 mil thick thickness, whereas silicone is more like 4. So again, double the thickness there. What happens with different types of parts, in this case, MELF components, metal electrode leadless face type components, and what happens is the conformal coat gets underneath the barrel of the component and the Z-axis expansion pushes up on it and can crack the glass. So, in this type of scenario, if you know you're going to coat, maybe you don't want to use MELF components. You can have the same type problem occur on a ball grid array. We had an assembly that was dip coated, has the BGA component. This part had passed accelerated life testing from -40 to 100, and then failed quickly in the field with cracked ball joints, as you can see in the lower right part of the image. What caused it was the fact that conformal coating got underneath the edges of the ball grid array and then had significant Z-axis expansion and pushed the component up and actually cracked several of the solder joints as a result of that. So there are things you can do to obviate that. You can use an underfill underneath the ball grid array, and then the conformal coat will be stopped by the underfill at the edges. You can put a bead of another type of adhesive around the edges of the component and edge bond that, and then conformal coat, and again, it won't get under the part. Those are two options, and either one of those will reduce the propensity for the conformal coat to get underneath the component and cause that Z-axis expansion. What happens is that when you go through the glass transition temperature of the material, and we'll talk about this both for conformal coating and potting, is that you can see in the lower left image on this slide, the blue trace is the coefficient of expansion going up as you pass from lower temperature to higher temperature. And at the same time, or almost at the same time, the modulus of the material is going down. What happens, though, is that the coefficient of expansion tends to initiate before the modulus tends to decrease. So what happens then is what's shown in the right-hand lower image, where there's a spike in the stress level that gets applied to components and the circuit board before dropping off as the modulus decreases. So that stress can crack solder joints, can crack components, can lift ball grid arrays, and crack solder joints. So, again, care needs to be taken in understanding the TG of the conformal coat or potting material that you've chosen. Usually our recommendation is to find a material whose TG is outside the operational min-max temperature range for your particular application. You can't always do that, but try, because that will eliminate this type of failure mode as an issue. This slide kind of gives you a little more insight into that. It's actually behavior of an acrylic conformal coating. And you can see that the glass transition temperature of this particular material is 5 to 15 degrees C. So below that point, the coefficient of expansion is 170 parts per million per degree C, but above the TG, it doubles to 340. But you can see that if you had a temperature range of operation of, say, 0 degrees C to 35 degrees C, and you passed back and forth from those two extremes, each time you pass through that CTE going to a higher temperature, you would double the amount of pressure being applied, and with the, because the expansion coefficient is twice as high. So that needs to be really considered in selecting your materials. One of the other things is sulfur and its impact on silicone as a conformal coating. We've seen numerous cases where the silicone is penetrated by sulfur in the air. And what happens is that over a period of time, the sulfur will penetrate the coating, get onto the surface of the circuit board, or hybrid in this case, and create dendritic growths or a black corrosion, and that will eventually short things out. This picture shows you a little bit better images of that black corrosion, and it will continue to build underneath the silicone material. So again, if you're in an environment, or you're going to be in an environment where your product's going to be exposed, then you likely want to think about using a different material than silicone. One of the other things that the same situation can impact are chip resistors. They have a metallization, in this case silver, that's underneath the resistive element on the top part of the resistor. And you can see in the blow-up that the sulfur attacks the silver, creates an open essentially after time, and creates a silver sulfide at that interface who goes up very highly in resistance and pretty much acts like an open. So, the resistor manufacturers are now creating parts that don't have an impact from this type of exposure. They use something like chromium instead of silver as the metallization under the resistive element. So if you know, again, that you might be in an environment where sulfur is going to impact you, use the other types of resistors. Some other failure modes. Capillary flow. This image shows some areas where you can see the fluorescing conformal coat, and some areas that are just the typical green solder mask on the board surface. And what happens here is that the conformal coat runs away from some areas to areas where it's easier to flow, and that could be completely under ball grid arrays, which would not be ideal. This is caused sometimes by low viscosity of the coating, or it could be due to too much coating being applied, or it could be due to the high surface tension of the coating that you're using and it's not flowing properly. So things to look into, if you see this type of defect. You can also get delamination, and this is where the conformal coating lifts from the board surface, like you can see in this image. And it's likely due to either cleanliness or an improper cure cycle. So if you see this, those are the types of things you need to explore. But one of the most difficult to deal with is cracking of the conformal coating. This could be due to a variety of reasons. It could be due to your cure cycle, where the temperature was too high or the cure cycle was too fast. Could be because you got too thick with the conformal coating, in this case thicker than 5 mils. And then what happens is that the coefficient of expansion of the conformal coating becomes a driver on the overall CTE of the assembly and can lead to cracking. Another possibility is that your environment, your use environment, is either too hot or too cold, which is causing the coating to flex and crack. And a fourth way that you can possibly have an issue is if when you're running your particular product, you heat up a chip resistor or another component very high, and that will eventually caramelize the conformal coating, and that'll lead to cracking in that area because the coating has really gotten hardened. And again, once you have those cracks, you have ingress paths for moisture, and that causes all the problems that we've talked about. Another problem is de-wetting, and this is where the coating refuses to adhere to the surface. This is kind of classic for no clean flux residues being left on a board. If your board is primarily just surface mount parts, the no clean flux residue from the solder paste is not super high, so it might be okay. What we see tend to happen is that when you go through either a wave soldering operation or a selective soldering operation, that the fluxing operation might be a little bit heavy, in which case you might send flux through the via, like you can see in this board, through that hole, and it'll get onto the other surface of the board, side of the board, and leave a residue there that will ultimately cause this type of de-wetting type activity. You can also get pinholes or bubbles, and this is air that's trapped under the coating. You can get a situation like this where you've again put on the coating too thick and bubbles can get trapped during that application. When you do have bubbles, it can drive microcondensation and therefore make electrochemical migration, or ECM, more likely. So, bubbles can be very detrimental to your assembly's performance. Orange peel, another issue with conformal coating. Where we usually see this occurring is if a spray nozzle is held too far away from the circuit board surface and it leaves kind of an inconsistent or insufficient coverage and the coating is not level. This can also occur if there's an incorrect cure profile, especially a fast profile being used. And you'll get this very irregular surface, which is not providing adequate protection to moisture. So masking, I mentioned earlier, and one of the things that you have to think about with masking is what approach are you going to use? And there are several. You can use liquid latex. This is a removable solder mask, if you will. And you apply that over areas on the board. Might be holes in the board where you don't want conformal coat to penetrate the holes because you're going to put a connector in there or wires into those holes later in the manufacturing flow. You can use masking boots like you see in the lower image on the right, and those masking boots protect individual components. They are manufactured for certain types of devices so that they form a good, relatively good seal at the board interface. You can use Kapton, or in the case of the picture on the upper right, different types of tape to seal off components. Having done a lot of boards with Kapton tape over the years, the one thing I can tell you is that it typically takes 2 layers of tape to provide an effective seal. And if you're doing a dipping process and you don't do that, the conformal coat has an amazing ability to penetrate even the smallest pinhole of a tape and get underneath it and either impact a component or a connector. And trying to clean it off the leads or pins of a connector is virtually impossible, so it requires rework. So taping, be very careful, but it's an approach that works. And the types of parts that usually need to be protected are switches or other types of electromechanical components, batteries, connectors, glass-bodied diodes like the MELFs I showed you earlier, optical type components, potentiometers, again, where you don't want the sweep mechanism of the pot to be affected. So masking, critical part of the process. This is also the most time-consuming portion of the conformal coating process, but it's absolutely necessary. Selecting the right material is also critical. For example, acrylic materials have a maximum operating temperature of 125 degrees C. So if your requirement was an automotive application, that likely would not be the best choice, because at the higher temperature of exposure in the automotive environment, you'd have an effect on how soft the coating gets, and that can cause some problems with exposure to either moisture or possibly petroleum residues. You might be better off in that type of situation with a silicone, again being aware of some of the sulfur issues, but it has a maximum temperature capability of 200 C, which is much more amenable to the automotive environment. A UV material might not be the best if you have high-profile components on the board. When you coat the board itself, you can leave areas unprotected on high-profile parts and create a shadowing type situation, and not get proper coating and sealing to protect the rest of the assembly from moisture. So again, choosing the right material as a function of your particular design and application is critical. So let's think a little bit about potting materials. They behave very similarly to conformal coating. Again, they're essentially to do the same function, to protect the electronics from environmental, chemical, mechanical, thermal types of stresses and issues with the what's in the air or what's close by to the product. And same thing, selecting the wrong material can cause a problem. Like the types of materials used for conformal coat, potting materials are made from polyurethanes, silicones, UV cured acrylics, some epoxy materials, and again, choosing the right one for your particular situation is what you need to pay very strict attention to. So you need to understand your thermal conditions, what your potting material is going to get exposed to. Typically, when you choose a potting, you might choose it based upon the min-max temperature of that material. But if you look at my example here, if you have a material with a 200 degrees C continuous rating, you could put it through a soldering operation for, say, lead-free assembly at 250 degrees C, and it would be just fine for that short burst of a few minutes. But if you recognize that you're exposing it to 250 and you choose a material that has that much higher temperature capability, you're going to pay a lot more for that conformal coat or potting material than you would otherwise. So again, understanding the manufacturing flow, the real-world application, and the selection of your material are all part of your responsibility. Again, curing process, big deal. One of the things with potting, because it's much, much thicker than conformal coating, if you're using a higher temperature cure cycle, there is usually an exothermic reaction involved when you cure these types of materials. And we've seen some situations where those temperatures have gone much higher than 200 degrees centigrade, particularly in fast cure environments where the temperature for the cure cycle is higher so that the time is shorter. That can damage components when you hit that type of level. So, it needs to be avoided if possible. Fast cures can also leave entrapped bubbles, which, as we've seen, can have an effect on electrochemical migration and moisture ingress. The more potting, the higher the risk associated with the exothermic reaction, especially if the thicknesses get greater than 1/4 to 1/2 inch. So care needs to be taken. What happens, excuse me, if your cycle is wrong? So we had a situation with a customer where they were using a potting material, and we actually tested the material and found out that its glass transition temperature was -22 and not -40 as advertised. This was problematic because their particular application went to a temperature in between -22 and -40, which brings us back to the issue of passing through the TG during a temp cycle. Not ideal. We also looked at this material and noted that the material still seemed very viscous even after it was supposed to be fully cured. In that lower right-hand image where the yellow arrow is pointing, you can see that there's, the potting is still not fully cured down very close to the board surface. What we noted was that this uncured material could also carry a current. And therefore, when a voltage was applied to the board, it was carrying a current from point to point where it was not supposed to be, and that eventually caused a breakdown failure of the product. So not getting a complete cure is also a potential damaging issue. Adhesion I've been talking about, and you really have to pay attention to it. Some potting materials have a low surface energy, and therefore they don't bond as well as you would hope to the surface. And so this brings, back to cleanliness and good surface treatment, maybe even a primer to get the adhesion you need. You can do things like modifications to your housing to let the cured potting lock itself and get better performance. And again, cleanliness is a key point that you have to pay attention to. Think about the flow. Viscosity then becomes the primary issue to consider. Geometry of the housing or the shell, is also important because of the flow that you've got of the material through the housing and how it's going to be able to move during the shrinkage in the cure cycle. Watch out for large horizontal surfaces. When they're filled from the top, they can entrap moisture, and that can affect your performance. So if I'm going to pick a potting material, what do I want to try to do? Ideally, the coefficient of expansion should be as close to that of the circuit board as possible, in the 20 to 30 parts per million per degree C. And you saw from some of my earlier numbers that that's hard to do. The larger the coefficient of expansion difference, the more you have to pay attention to the modulus of the potting material to limit the stresses that get imparted to the circuit board and the components. So you'd want to choose, if you were going to have a higher coefficient of expansion, you'd want to look for something that has a more compliant potting capability and a lower modulus. Key point, too, is that if you've got a housing, you want to try to keep the hydrostatic pressure in the housing equal on all sides of the board. We see a lot of situations where the potting might be 1/2 to 1 inch thick on one side of the board and less than 1/4 inch thick on the other side of the board. What that does is it creates a scenario for excessive warping, and that warping can drive failure. So you may have to look at modifications to your housing, and also the material that it's made out of might need to be relatively stiff so that it doesn't give during expansion and contraction type situations. Just like I showed earlier with conformal coating, potting compounds behave very similarly, where as the coefficient of expansion goes up, the modulus goes down, and behaves in a very similar type fashion. solder stresses that can occur become very high during a cold dwell of a thermal cycle when you're dealing with potting materials. And you can see here the amount of megapascals of stress is essentially double or even 3 times worse during a cold cycle than it is during the hot cycle. If we look here with respect to creep strains, which it's known where if you have higher creep strains, the time to failure is significantly reduced. But here you can see that in the unpotted arrangement, the hot cycle provided more of an impact on the strain, whereas in a potted environment, the cold cycle created more of a stress with respect to excessive creep. And because the more energy is required to cause that cold temperature creep, more damage occurs to your parts and solder joints. This is just a detailed definition of what creep strain is, but in a nutshell, it's the tendency of a material to move or deform permanently under the influence of stresses. We've seen where conformal coating or potting can actually move solder under these types of stresses to a point where it causes a short between leads on components. So understanding, creep is also a critical parameter. So kind of to wrap this part of things up, you need to pay attention to the glass transition temperature. You need to understand the modulus and coefficient of expansion of your potting material and know what it is both below and above the glass transition temperature. Key points. What you're going to find is that most data sheets don't have all that information. So you're going to have to contact the supplier of the conformal coating or potting and ask those questions. You need to design your housing. You want to make sure that you, where the potting material might pull against itself when shrinking, which can cause PCB warpage due to the housing. So again, you want to make that hydrostatic situation as much as possible the way that you can create a situation where equal pressure is on all sides of the circuit board. This is just kind of a quick thing to show what the potential mechanical benefits are of, in this example, a model where I used 5 millimeters of potting covering the entire board surface, and it more than doubled the natural frequencies, which has distinct benefits when you're dealing with vibration and shock environments. So potting can do quite a bit for you in that type of situation. So let's talk super hydrophobic materials for a few minutes. These are the newer materials. They've now been out on the market for something more than 5 years. These are the ones where you see where the cell phones can be dropped into water and nothing happens. They are truly much better at moisture proofing than the current conformal coats. What you're looking at with superhydrophobicity is that the wetting angle is greater than 90 degrees. And in some cases, I've seen materials that are as high as 120. So water beads up, rolls off. Moisture doesn't tend, even in the case of humidity in the air, doesn't tend to break down these materials and penetrate. Quite a number of players. I'm not sure that I have actually got all of them. I think there are some others that are also making different types of materials. Most use some form of chemical vapor deposition. DFR has worked with P2I, Semblant, and NeverWet. NeverWet actually has moved away from the electronics industry and is coating mechanical things. For example, they got the project to do the steps of the Eiffel Tower so that the steps are never wet. So, but there are a lot of companies that are doing things. NanoSlick is a spray approach. Some of the others here, like I mentioned, are vapor deposition. So you have to look at that cost vis-a-vis warranty period versus getting rid of some of the processing associated with masking and see if that cost trade-off makes sense to you. So, hydrophobicity, again, it's CVD processes, low vacuum requirements, room temperature type processing, variety of different nanomaterials, and some different particles in them to make them super hydrophobic. We looked at perylene, again, one of the original types of materials. The thickness tends to be about 1 micron, and that's to make sure that you get pin-free or pinhole-free action. And then your super hydrophobic materials, though, these coatings can be pinhole-free down to 100 nanometers. They can facilitate, in some, not all cases, optical transparency for inspection, reworkability, and one of the things that's a key feature is the elimination of masking. So if we look at this information courtesy of Semblant, you can see that the low-level contact resistance, whether you're coated or not, is essentially the same. So ideally, that means that you've gotten your coating on the board surface, but it didn't require significant masking for the connector once brought together to maintain the appropriate levels of resistance. So it's a nice situation to be in. Some of the issues. These materials, from what DFR has been able to see, have lower voltage breakdown levels than some of the older coatings, and that can be a potential issue with respect to MIL or IPC specs. Some of the materials are translucent and not transparent. So that means that inspection is more difficult and challenging. Cost, because it's CVD processes in many cases, is more expensive than some of the common coating materials. Very, very comparable to that of perylene. But some of the different cell phone manufacturers are noting that their return on investment is there because they're getting a significant drop in warranty costs. The throughput for these types of materials is typically a batch, the vapor deposition chamber, and coating times tend to be, say, 10 to 30 minutes. So that, again, is a time adder to your manufacturing flow, depending upon the amount of thickness. It is being used in the cell phone world, so it has been adapted for high volume manufacturing. So to wrap things up, there's just significant opportunity for improved field performance when you're dealing with conformal coating and potting materials. Might lead to cost reductions for you as a function of warranty and less failure issues to deal with. It does require that you have a knowledge of the materials and processes that are available to you to use, the differences in their behavior when exposed to the different types of environments that are out there in the field. And one of the key things that we look at from DFR's perspective is to not rely on standard qualification tests for these different types of materials, but to look at a testing approach that's based on physics of failure. And by that, I mean an approach where you understand the potential causes of failure for the different components and your circuit board in the environment where you're planning on putting it, and then devise a test plan that assesses whether or not your product is going to encounter those types of physics of failure situations during the test, but at the same token, you're not overstressing the product to a point where you break something that will never be seen in the field, because that doesn't gain anything for you.